I love reading another good LoRa paper. We just keep on getting better and better LoRas. Sooner or later, we're gonna have like the best LoRa. Gonna be able to like train an entire model with just a LoRa and like 1 bit of precision. No, kidding. Anyways, QA-LoRa, it's another version of LoRa. It's a continuation of QLoRa, which is a continuation of LoRa. So LoRa is the initial PEFT module. That's how you fine tune using low rank adapters, and it's very efficient. It's very good. Everyone loves LoRa. QLoRa made that more efficient by quantizing the original weights, and QA-LoRa basically wants to uh, not improve the LoRa itself, but improve the accuracy after you do the LoRa fine tuning. So yeah, we'll get into all that. So it's a cool paper. So quantization-aware, low-rank adaptation of large language models. So first off, what is LoRa? I will go quickly through LoRa in case you're not familiar with it. So basically, if you have this LLM, actually it doesn't even have to be an LLM. If you have, say, a vector, we will call this x, and x is of dimensionality d. Then you train something. So usually you train a large language model, and large language models have feed-forward layers, and feed-forward layers are just composed of weight matrices. So you have this weight matrix here. This is going to be called W, and W, let's just say, is in RD by, it can be anything. It can be, say, I don't know, F. It's not very good notation, whatever. D by F. So you basically have this matrix, just transformation, and then you get Y in RF. Pretty obvious. This is just a linear layer, so Y is equal to WX. Now, once you have this trained, so you have this large language model that already has learned, like Llama or GPT-3, it's learned all about the internet. Maybe you want to fine tune it on something. For example, maybe I want it to parse medical data or something like that. Then what you do is, well, you can just train it like this. However, in practice, it doesn't work that well. If you just train this weight matrix here, you maybe have to mess with the learning rate a lot. It usually doesn't work out if you just directly train this weight matrix. Now, what we can do instead is freeze this weight matrix so it keeps the knowledge that it previously had, and then we can add a new weight matrix that basically changes that knowledge, but it still retains this old weight. So we can basically add a new weight here, and actually, you can, what LoRa does is it adds 2 weight matrices. So we will call this weight matrix here. This will be A, and A is of dimensionality D by R. Now we have a second weight matrix here, and this matrix here is B in R by F. Yeah, it's of dimensionality R by F. And R here is going to be a lot less than D usually. So let's say D is equal to 512. This is like BERT, for example. Usually this is a lot larger, like 2048 or something like that. Then you can make R equal to 16. It seems to be pretty good, but you can even make it 1 and it works pretty well. So basically, you have these 2 matrices here. You have your A matrix, which is, in this case, it would be a 512 by 16 matrix, and then B would be 16 by 512. We'll say F is equal to D because it makes it easy for me, 512. Now, what you do is you send X through the A and B layers, or you multiply it by that, and you get this new output, which is WX plus ABX. And you usually initialize B to all zeros so that the output remains the same whenever you initialize it. So this term basically isn't there until it starts training. And then as it starts training, it starts to update this. And I'll actually make this blue to show that it does not change. So W doesn't change, and you're just changing these matrices. Now, the reason you have these low rank matrices where you have this little r is because training with a full rank matrix is first off, it takes up a ton of memory, and that's just not good. It's just, you can't fit that on a GPU. But you use LoRa because you can make a small R and you can fit it on your GPU better. Let's say we just initialized this to a full matrix, which I'll call W2, which is an R of 512 by 512. So in memory, you're going to have to store this whole 512 by 512 matrix, and that's a lot. So 512 by 512, you have to store all these weights. However, with LoRa, you only need to store 2 times 16 by 512 weights in memory, which is a lot less. And if it can do the exact same, if it can get the exact same performance, then that's a bonus because you're storing a lot less. You're storing a lot less data in RAM, and you can train it a lot more efficiently, so faster. But you can also train it on a much smaller GPU, which is always a bonus. And you can now train these llama models on, or fine tune these llama models on, say, one GPU. So this is what you do. And once you're done with this, you have this combination here. Once you're done with this, you have your weights, your old weights, which were frozen, and you have your new LoRa weights. Now, we can combine these together to make one weight matrix. So if we move x out, then we have x times w plus ab. And if we define w hat is equal to w plus ab, then our new output is just w hat x. And we just store this in memory. So you don't even have to store more data whenever you're done fine-tuning this thing, which is another bonus of LoRa. Now, this is just normal LoRa. What QLoRa does is it basically quantizes this W. So what is quantization? So if we had, say, this vector here, this vector is, say, well, I guess this can be like our span of values. So let's say we have a span of values from 0 to 256, or 0 to 255. Now this can be like an int 8. So int 8 can take on any values between 0 and 255. So maybe you're doing computations in int 8 and you want to quantize it. Now quantizing this to, say, an int 4, I guess that would be a lot smaller, but we'll draw it like this. Int 4, which can take on values from 0 to 16, I think. Yeah, 16. Basically, what you're going to do is you're going to bucket your int 8 into 16 bins. So you're going to bucket your values from 0 to 255 into 16 bins. So we can do this uniformly. Let's say we just do it like this. We just bucket it into 16 bins. That's not 16, but whatever. You get the idea. And then you basically group the buckets into one value. So this one here, we'll start from the bottom. This one here, let's say that's going to be 0. So any values from 0 to 16 now become the value 0. And then we do that for the second values, or the second set of values as well. So any values from 0 to 15, 16 to 31, 16 to 31 will become 1. And that's all you're doing. You're basically just grouping these values together to make it more compact. So now you're just storing it in int 4 instead of an int 8. And hopefully the information is close enough for the computations you're trying to doing. And this usually works well. And then you can transform it back by saying, okay, let's just say this value 0, if we want to transform, so this is our int 8. And then this is our int 4. If we transform it back to 16, then all the values that are 0 will become, say, 0, and all the values that are 1 will, say, become 16. So this transforms it back to int 8. So we can transform it back, and it is hopefully a close enough value for us to do our operations with. Now they define this more mathematically over here, and I will give an example. So this here is how you may quantize it. So remember, we want to quantize our weight matrix. And we're going to do that through this quantization procedure. And I'll show you why you want to quantize this in a sec. But basically, you want to store this weight matrix in a smaller set of memory. So usually you have a float 16. Maybe you want to store this in, say, an int 8. So then you only have half the memory that you're storing to do computations with this matrix. Now, if you want to skip this, go ahead, if you already know how quantization works. But I'm going to go through a real quick example of quantizing, say, a weight matrix here, and just show you that it does work well. Like it does work good enough. So like say we had this weight matrix here, and this weight matrix has values from 0 to 7. So this will be 3-bit. And let's say we want to convert it to 2-bit. So that'll be values from 0 to 3. Now to do this, we follow this operation here. You have your weight matrix. So this is your original weights. And then you compute your alpha. Your alpha is your min or your max value minus your min value divided by the number of bins. So basically your range divided by the number of bins you have. So what values does it span? And then I basically group that. So this is basically the number of groups you're going to have. In this case, it would be 16 groups here. I don't know. This is the group size. So in this case, it would be, is that 16? I think that may be 16. But whatever 256 divided by 16 is, I think that's 16. So it's your group size, and this is your range, this is the number of groups, and this is the group size. So if we actually shifted this to say, like if we just added 10 to 265, and then this was 10, then this will still work because we have this b value. As b value is just the minimum value, so this takes care of the shift operation. And basically what we're going to do is we're going to take our weights. So if this was 265 to 10, then we're going to take our weights, we're going to zero it. So we're going to convert it to 0, where the lowest value is 0, and we shift all the weights in that direction. And then we basically divide all the weights by the group size, so by this size here. And that'll give you a value between 0 and the next step. So instead of this being 0 to 255, it'll be 0 to, this is 0 to 15, not 16, 0 to 15. And and this will be 1. So this first group here will have decimal values between 0 and 1. Then what you do is you round that, and then you have your quantized version. So these values here, once they're rounded, will all be 0 or 1. Depends on how you round. If you do floor operation, then all these values will be 0. And then you have your quantized values. Now you can unquantize it by simply multiplying by alpha, which is just undoing this operation, and then adding beta, and that's just undoing this top operation here. And that will give you what I showed over here. It's like a good representation of what you initially had. The best representation you can do by only storing one value, or two values, alpha and beta, along with your quantized weight matrix. And here's a little example if you want to look at more intuition behind that. But that's a long explanation of quantization. Now, QLoRa basically takes this weight matrix here and it quantizes it. Let me go over here. So QLoRa quantizes your original weights, and then upon doing the operation, it unquantizes it. So you store it in memory as this quantized version, and then whenever you store it in as this here, this thing here, this entire matrix here, this quantized version, you store that in memory. And then whenever you need to do an operation with it, since your A and B here they're not, say, an int 4, they're not quantized. They're going to be floating point 8, floating point 16. Well, these are int 8 or int 4. you need to unquantize them so you can do an operation with float 16 values. X is also floating point 16. So you unquantize int4. You unquantize these using this up here, and then you do the operation. So that's QLoRa. And the reason you do that is because you can store you only need to convert these to floating point 16. So you only need to convert these whenever you need to use them. If you don't need to use them, then they're in memory as a int4. So that's better than here, where if you don't need the values, then they're in memory as a floating point 16. So that's the difference between QLoRa and LoRa. All you're doing is quantizing this weight and unquantizing it as you need. So LoRa and QLoRa. Now, what you usually do is after you do QLoRa, you have to merge these weights, right? Now, whenever you merge these weights, you convert this to a floating point 16. So you unquantize this, and then you merge the weights like I showed before, where you do W hat is equal to, in this case, it's W tilde, the quantized weights. So W tilde is the quantized weights, W are the normal weights. So you convert W tilde to W, which are your original weights, at least your approximation of them, because you can only do so much by unquantizing. So your approximation of the original weights, and then you add A and B, and that's your W hat. And you have to unquantize W so you can store W hat. You can't, if you were to quantize this, then you may run into issues. And this is the problem. You have to store W hat as either a floating point 16, which takes up a lot of memory, and then quantize that. So whenever you're done fine-tuning, you want to do inference on this thing. Whenever you do inference, you want to convert your floating point weights into your floating point 16 weights into quantized int4 representations. Now, because you store your weights as floating point 16s, because that's the best precision you have to quantize that to an int4. And quantizing that to an int4, they claim doesn't do too well. And this is called, they have it over here, PTQ, post-training quantization. So after you're done with QLoRa, you have your weights stored as floating point 16s, and then you need to do quantization on those floating point 16 weights to get your, so that you can do inference in an efficient way. However, they claim that that runs into problems by quantizing after training. And what they want to do is while you're doing your fine tuning, they want to basically have the algorithm, have the model learn how to do kind of its own quantization. You need to have it learn the quantization so that the outputs are as fit as possible for the quantized weights whenever you quantize them. So that's the idea here. It's saying, so here, this is inference. Inference, you have this floating point 16 weight after fine-tuning, and then you do post-training quantization to get your int4 weights. So this would be your W hat, and this would be, I don't know, W prime maybe, your quantized version of W hat. Maybe we'll call this W hat Q. Meanwhile, what they want to do is right after you do your LoRa fine-tuning, they want you to have W hat Q. So you skip this middle step where you have to quantize a second time, and you only quantize one time. So the model basically learns the quantization. It knows the quantization, thus quantization-aware. So that is the idea. So let's, and they proposed two ways. The first way they said failed, so we won't even look at that. The second way, they said the second way seems to work pretty well, and it's a pretty simple idea. So we will look at this. So let me erase this. So the basic idea is we want the model to learn the quantization. So we want this output matrix here to be able to be quantized. And what they see is, I'll go here. What they see is whenever you're doing the merging, so W hat is equal to, I have stuff written out over here. So basically your W hat is equal to, we're going to call this our quantized weights. So our quantized weights are equal to this here. So they kind of change it a little bit. You can do this change, W alpha plus beta. So you can do this change where instead of up here, you did W minus beta over alpha. You can change this to W minus beta over alpha, and then you do your rounding. You can round W alpha and then just add beta, so it's fine. Now, these are your quantized weights. And then to unquantize them, W tilde, you basically subtract beta. So it's W hat minus beta, and you multiply by alpha. So that's alpha times W hat minus beta. And you can see that that'll give you your approximation of the original W, alpha times W over your quantized version, your rounded version of W over alpha minus beta. So these cancel, and you get alpha times your rounded version of W over alpha, which is approximately equal to W. So keep this in mind. W hat is the quantized version, so this would be your int 4, and W tilde is your unquantized version. However, it's your approximation. So this will be your floating point 16. So you go from floating point 16, you quantize it to int4, and then you can undo that using these formulas here. Let me expand. Yeah, so that's just your weights. Now, if we look at the output, so they call it result, I'll just call it out. And if we look at out is equal to Wx plus, there's also this term here, S. We're not going to worry about S because it's just some constant, ABX. So that's our output. And whenever you do quantization, this will be W tilde X approximately plus ABX. And this is equal to X times W tilde plus AB. And this is what we want to work with. Now, if we expand W tilde, let's just get rid of X. And let's just look at the weights. So if we look at W tilde plus AB, and we expand W tilde to this up here, then we get alpha times W hat minus beta plus AB. Now, if we look at this, right here. Yes, yeah, so if we look at this, then we can do W hat times alpha, so alpha W hat minus alpha beta plus AB. Then you can kind of look at this as alpha W hat minus, say, we'll call this beta hat plus, say, I don't know, AB. Yeah, AB. And you look at this expression, you can kind of think of this part here as just like a new beta. So you combine these together. So you have your original W, and you can kind of combine these together. Now what they do is, yeah, so they basically, I mean, that's kind of what you can look at this and you can see that you can combine these together. And we'll get to why you would do that in a second. But the basic idea is, what if we just kind of let the LoRa values be our beta? So what if our LoRa values can be combined in such a way that we get that it is our beta value? Now, if we do that, then we would get something like this. Alpha is equal to W hat. And we want to subtract beta from there, so minus beta prime. And we'll say beta prime is equal to that here. So this is our expression. And this expression is the same as the unquantization formula. The unquantization formula is just alpha times W hat minus beta. I mean, we would have to multiply this by alpha still, but that's fine. We'll work with that. So we'll get to how you would actually like do something like this in a sec. But the basic idea is, what if we let the LoRa values kind of be the unquantization parameters beta. Now, the way they do this is they kind of have this trade-off here. So if we go all the way back up here, you have your quantized weights, you have your LoRa. Now, they show that your quantized weights are usually, like what I showed up here, is you usually have one beta and one alpha for your entire weight matrix. That's actually not true. You usually have one beta and one alpha for each row or column. So I have a drawing over here. You usually have one column, and your column, each of your columns have a alpha and a beta. And each of your columns are going to be basically it's going to be a linear combination of x. So basically you quantize each of the rows in here, depending on how you look at it. And you quantize those individually. Now, they kind of mention that there's a problem with doing that. So if you do that, and you want your alpha, or you want your A and B to basically be able to be merged, then this just doesn't work out. And the reason it doesn't is, I say down here, this mess here. If we want to keep the property for quantization, we must guarantee that for any j, so for any of the outputs, all possible values of Cij, so that is our Cij is the output of the LoRa, form an arithmetic set with a common difference being alpha j. So an arithmetic set is a set where each of the values has the same difference. So 1, 2, 3, 4, 5 is an arithmetic set with a difference of 1, and 1 would be alpha j. However, they say this is intractable in continuous and gradient-based optimization unless we ask that Cij is a constant, i.e. they're all the same for all I, or for all j. This is equivalent to set all row vectors A to be the same. So you're setting all the row vectors to be the same because you need this property. And then they say the above strategy, while tractable, leads to a significant accuracy drop in practice. And that's because all the rows of A being the same vector has a rank of 1, and thus AB is equal to 1, the rank of that. So that's the initial problem. However, they kind of change the idea a little bit, and they say they partition each column of W into L groups. For ease of implementation, we set L to be a divisor and D in. So if we look at our weight matrix here, so this is our original weight matrix, not our LoRa's. We already separate it by J. So we already have an alpha and a beta for all J, but instead, instead of just doing it for each J, so instead of having it look like this, I kind of erased everything, but having one column have their own alpha and beta, then you group it. Say you group the J. So this part here, G1, would have its own alpha and beta. And you can think of each group being also grouping your input values, X. And you kind of have this trade-off between, say, if we only had J, alpha, and betas, then your quantization can only be as good as your number of J values. The more alpha and betas you have, the more your quantization can be unquantized back to the original version. So let's say we had an alpha. Let's say we quantize, go to the extreme case where we quantize our weight matrix that we have an alpha and a beta. So we basically quantize each scalar independently. So if we were to quantize this value alone, then unquantizing it will result in the exact same value because we have an alpha and beta that tell us how to shift the value and the multiplicative value. Now let's go to the other extreme. If we had an alpha and beta for the entire matrix, then we have the worst case where we have the worst quantization we can have, where we have one alpha and beta, which shift it and scale and do the unquantization. And that's why we divide it into J different, we quantize it J times, and they get even more specific and they say, well, what if we quantize it not just J times, but we quantize it L times, L for each J. So basically we're going to have, so you split each row, this is actually each column, oh no, never mind, yeah, each row of W is split into L groups. Each group column has its own alpha and beta parameters, and each group needs the same value. Thus, so we're going to get to this in a second. So basically, we have an alpha, or we have alphas and betas that are of shape L by D out. So D out is J. So this is D out. This is our output dimensionality, and this is D in, and you split D in by L. This is actually, yeah, so we have three groups, and that's how many alpha and betas we're going to have. So instead of going to any of the extreme cases, we're going to have an intermediate case, and in this case, we're going to have an alpha beta for every two values in this specific case that I'm showing right here. They pick different L's, and they kind of experiment with that, but the higher your L, the more groups you have, the better your unquantization will do. The lower it is, the worse your unquantization will do. So that's the idea that they have here. And whenever you split this into groups, you add your x. So you have your x here, and you basically group your x. So like I showed down here, you have your group values here, and or you have your group values in your original weight matrix here. And if this is x, you also need to group these values. And you group them according to how you group your weight matrix. So you can see the correspondence here. Just matrix multiplication, you can see the correspondence there. This goes with I. So this goes with the number of groups. You just divide your x by the number of groups. So we do that here. We have our x, we divide it into the number of groups, and then they go on to say that you need to sum up the values in those groups. And the reason you do that will be apparent whenever we're doing the merging of A and B and the W tilde. So whenever you merge these, there's a reason they sum up these the values in X. We will get to that. But yeah, you basically sum up the values, the groups of X. So this would be, say, group 1, group 2, group 3. I guess I should do it the other way. Group 1, group 2. And these weights here would say be group 1, group 2, and then you would make another group and so on, like so. So you sum this up, and then you get your L groups. So this this group here will become a single scalar via the sum. And now your A matrix is no longer D in by R. They call R D int. It is now L by R. D out stays the same, or B stays the same, so it's R by D out, by your out dimensionality. or dint, depending on what paper you're reading, or depending on how you want to look at the notation. So this allows you to make a smaller A matrix as well, which is a bonus, but that's not the main reason they do this. So basically, you're grouping your W, you're grouping it, and you're going to have an alpha and beta for each group. So you have an alpha, a beta, you have an alpha, a beta, and this can unquantize each group independently of each other. So you're only quantizing groups of W, not the entire W independently, or not the entire W with a single alpha and beta. So that's the first thing. Now, when you do this, and you look at the code, then whenever you do this in the code, then this is what the forward method looks like. So the forward method, basically we quantize W. So pre-quantization, you quantize W. This is the quantized version here, and then you unquantize W. In reality, you're going to quantize it, and then you're going to store this here. Because there's no reason to quantize it and then unquantize it. That defeats the purpose. So you're going to quantize it using this here. So you're going to store W hat, and then you're going to unquantize it whenever you need this matrix, like we said with QLoRa. So you store W hat in memory, and then you unquantize W hat according to the alpha and beta parameters. And remember, the alpha beta parameters are matrices of shape L by D out. These are your alphas and betas for each group. So you unquantize this according to the alphas and betas in each group. I guess, yeah, so you just unquantize it using those values. Then you get W tilde after you unquantize your values. And once you get W tilde, you can now do X times W tilde. So this right now is just QLoRa with except you do a little bit more quantization to W. Now, they have this extra part here, this blue part here. It's a little confusing why they do like an average pool and then they multiply by this value. But basically, dn divided by L is equal to the number of groups, or group size. So if we had our X here, and let's say our X had 6 values, and we group it into 2s, so L is equal to 3, then our group size would be equal to 2. Group size is equal to 2, so that's just this value here. And that's this. So basically, they have an average pool 1D, and what average pool 1D is, it'll take the average of these values, but then you multiply by the group size, so you're actually just taking the sum. Yeah, so I mean, they could have just done that, but yeah, you're just taking the sum of these first 2 values here. So these first 2 values create a single value here. The second 2 creates another value, and the third 2 create another value. And these values are just sums. They're not averages. So you take the average and then you multiply by whatever you average by, which just gives you a sum. So all you're doing is taking a sum of the of each group. So each group is summed, or each part of the groups are summed, so you get a vector of shape L. Now our A-LoRa is of shape L by R, and our B-LoRa is of shape R by L, and then we have S. Don't worry about S. S doesn't really matter. So multiplying these together, sorry, not R by L, R by D out. So multiplying these together, so multiplying your summed X, your, I guess, kind of quantized X by your A matrix and your B matrix results in a vector of shape D out. And then you sum those together. So basically all you're doing extra is you're changing LoRa A so that it's of shape L by R instead of Dn by R. And you're summing up the groups you're doing a sum along the groups in X. Yeah, and then that's how you get your result. Now, why would you do this? So the biggest reason you would do something like this is because A and B can be any value. So once you already have trained W, so W is already trained. Once you've already trained W, you know those weights are changing, so it's super easy to quantize. But how do I quantize a value that can be anywhere in the range of floating point 16? That's some massive range. How do you quantize that? It's almost impossible to quantize. But here's the thing. Whenever we're moving W back, so whenever we're getting W tilde is equal to alpha times W hat minus beta, here's one thing to notice. Alpha and beta are floating point 16 values. And these are just of shape L by D out. And if L is small, then these can just be of shape, say, D out. So this is just like these are smaller matrices of type floating point 16. And side note, if you saw a QLoRa video, you can actually quantize these weights. But yeah, back to this. You basically store your alpha and your beta as floating point 16 values. Now, since our LoRa values are floating point 16, then why not just store our LoRa values as our beta value whenever we're done with it? So we do the operation here, and what we're going to do is we're going to create a new beta value such that whenever you do the unquantization with this new beta parameter, it gives you this here. So I'll show you how. So this here is, so once you're done with training, so you do this loop here with QLoRa forward. When you're done with training, you have your betas, you have your alphas, and these are of shape R by L by D out. Now what we can do is we can, right here, we can take our LoRa's, so let me just write that out over here. So we have A is in R of L by D, L by R. B is in R of R by D out. And alpha beta are in R of L by D out. Now, we can basically create a new beta. So let's call this beta hat is equal to, this beta hat has nothing to do with the previous beta hats I've mentioned before. But we're going to say beta hat, so our new beta value, is equal to beta. So these are our betas that we had for unquantizing W. So beta, and then we do minus alpha or minus AB over alpha. So this is our magic merge here. And we can store these as floating point 16s. So now we don't need beta. We don't need to store beta anymore, and we can instead store these values here. And since we already had to store beta in the first place, then this doesn't add any extra space. Like this doesn't take up any more space because we merged these together. So yeah, this would be AB. So that would be L by R by D out, which goes to L by D out, in case you're skeptical of this. So you can merge the weights by merging them into this new beta parameter. Now during inference, whenever we have an x, so x is in R of dn, whenever we have a new x, we need to do this matrix multiplication. And we know that y is equal to wx plus AB x. So we know that, which is equal to w hat x. So we know this. Now how do we do this? How do we do this inference procedure with our new beta? So right out up here, after we've merged this, we can actually merge this into a single weight matrix to do the computation. So you store your weights as you store your weights W, say W. You store these as int 8s, int 4s, or whatever you want to store it as. Maybe int 3, maybe int 2. They do all three of these. You store your alphas and your betas, your beta hats, as floating point 16. So this is your model. Your model is now your W hats, your quantized W's, and your alphas and betas, your alphas and your merged betas, telling you how to unquantize W hat into W tilde. Now, we know W hat is equal to, just to show you, if we add this beta parameter, it does give us what we would want. So let's say we have this here. So we know W hat is equal to this. And let's call this, we'll call this W tilde. W tilde is our unquantized version. We know W tilde is equal to W hat minus beta. And in this case, it's not minus beta. It is minus beta hat plus alpha. So we're adding beta hat instead, or times alpha. Instead, we're adding beta hat instead of our normal beta. And we can expand W hat. So it looks like this. So we have W over alpha plus beta. And then we're also going to expand our beta tilde. So beta tilde is expanded to what we have up here. That's beta minus AB alpha, AB over alpha. And we multiply this by alpha. Now, if we kind of, let's move the negative sign through, and we have W over alpha plus beta minus beta plus AB over alpha, all this times alpha. Now these betas cancel out, and you end up with round your original weights times alpha plus AB over alpha times alpha, which is just AB. We'll make this red, plus AB, which is approximately W plus AB, which is how we do LoRa normally. Yeah, so when I initially recorded this, I said I would talk about why X is summed, which I never talked about. So, real quick, the reason why X is summed is because you can't just merge it like this. There's actually one extra step, and that is, go up here. This isn't actually A, B. It's not actually it's not actually plus AB. It's A dot repeat. And you repeat this group size times B. So this basically, so your W matrix is in R of D in by D out, but your A matrix is in L, where L was derived from Dn. So A needs to go from L by D out, or L by R, to, and you need to repeat this multiple times. So basically, you have this vector here. Let's say it's a vector. If this is our first value here, then you would need to repeat your first value group size times, and then your second value group size times. And the reason you do the sum is because whenever you repeat it, you are basically having that value multiple times. And this is representative of the sum. So you're actually doing this computation, say, 4 times or whatever. So if our group size was, say, equal to 4, then you do the sum here, because whenever you're training, you basically need to emulate that you have this here 4 times if our group size is equal to 4. You basically have this here group size times, which is why you need to do the sum. Otherwise, you could just do a mean if you didn't have to repeat this. But since you do have to repeat this whenever you're doing the unquantization procedure, you do a sum instead of an average. So that's why. I just wanted to mention that real quick. So yeah, back to me from like 10 minutes ago. So using this beta tilde here, or sorry, using beta hat, which is our merged version of LoRa, we get to this formula here where if we add beta hat, it was formalized in this way. It was made to do this. If you add beta hat to, or subtract beta hat from W hat, then you get LoRa, a normal LoRa. So that's the idea. What you do is you store these in memory. So you're done training, you train using this methodology here. When you're done training, you store these in memory. You store these in memory somewhere. I am just going to store my llama weights, basically. Store your fine-tune weights. And then whenever you're doing an unquantization, you unquantize it using the normal formula, W hat minus beta hat times alpha, because you have those weights, you have those stored. So then you basically have a quantized weight representation and a way to unquantize it. And remember, our model learned beta hat, so that means that this is learned. And that is the idea. The idea is you basically merge your LoRa weights into beta, which is an unquantization parameter, so that you efficiently both store your parameters whenever it's done, and you can unquantize your parameters using your learned beta hat, because beta hat is parameterized by A and B. That is the big idea. I hope that makes sense. But yeah, you basically have your model that learned how to store things as an int4, or int3 or int2, which is the goal. The goal was to have the model learn this output. It was to not use this intermediate representation. And yeah, that's the idea. So let's see some results. Let's go down here. Now, you can look through these results more thoroughly if you want, but we have QLoRa and we have QA-LoRa. And if we look, QA-LoRa just does better. And if you look here, these are the number of bits, 4, 3, and 2. It's kind of cool to see that QLoRa, or QA-LoRa, does as well, or almost as well, in almost all cases, with just 3 bits. That means we can do inference with 3 bits. Let's go. 3-bit LoRa, yes. And also 2 bits. It doesn't do as well with 2 bits, but it does seem to do really well with 3 bits. So now we can do inference with 3 bits, as opposed to only doing it with 4 bits. And even with 4 bits, it does better. So QLoRa, it's significantly worse. With 4 bits, they're comparable. QA-LoRa does better than QLoRa with 4 bits, but like that. QA-LoRa does better than QLoRa with 4 bits, but the difference really shines with 3 bits. I think with 3 bits, it's a massive difference for most of these. QLoRa does not do well with 3 bits. QA-LoRa does, and it does okay with 2 bits. Imagine having just a 2-bit model inference. I think I joked about that when I talked about LoRa initially. Well, I think I said 1 bit. They should have done 1 bit. That would have been funny to look at. But yeah, it does well in general, just with 4, 3, 2 bits. Not as well with 2 bits, but it does a lot better. In this case, it actually did pretty good with 2 bits. Now, what about the time it takes to what about the time and the memory requirements? So what do they have here? The number of learnable parameters and time cost of QLoRa versus QA-LoRa during the fine-tuning stage. So if we look here, it's not just better in terms of accuracy. It has less parameters, QA-LoRa, but it also takes less time because it has less parameters. And that's because you're A matrix here is smaller, even though you're storing alphas and betas for your W tota, since A is going to be a lot smaller, since you have a small L, then you store less parameters in general, which is what they show here. And the final thing I want to show off is different group sizes. So different Ls. A larger group size means that you have less groups, which means you have less information. So a larger group size is worse because that means your group size is larger. And a larger group size means that your alpha and beta have to cover more. It basically has to cover more information. So your alpha and beta are unquantizing more values, which is less. It's not going to be as good because it's doing that. It's not going to be as accurate because your one values have to store information for more values. Yeah. So if we look here, 128, that would be the worst. 32, that would be the best out of these three. If we look here, it isn't too much of a difference. You can see that 32 groups, meaning that you have smaller group sizes, definitely group size. Yeah, this is group size, not L. That's not L. Group size. Yeah, so the larger your group size, the more your alphas and betas have to cover. So a larger group size obviously does worse because your alphas and betas are going to be less accurate to what your original data was, which is clearly seen here. But it's not that much worse. Like having less alphas or having a larger group size isn't too much worse. And it's a trade-off. The larger your group size, the less data you're going to have to store, but the worse your model is going to perform. The smaller your group size, the better your model is probably going to perform. I guess not in this case, but the more data you're going to have to store. So it's a trade-off that you have to make. And yeah, there's more things. There's also this part here. They're like, I don't know. If you want to merge for inference, it does not look that good right here, but that's the paper. Yep. I personally think that this is a pretty cool idea to have a kind of learn the quantization. And I mean, it definitely shows that it works pretty well. So it'll be interesting to see if this is the new thing to use.